So dear students, in the previous video we see about the losses and efficiency of the DC motors. So now in this video we will see about the various tests on DC machines. So what are the various tests on the DC machines are? The first one is brake test, and the second one is Swinburne's test, and the third one is Hopkinson's test, and the fourth one is field test, and the fifth one is retardation test. What are those five types of tests? Brake test, Swinburne's test, Hopkinson's test, field test, and retardation test. So in this video we will see about the brake test and Swinburne's test and the just connection diagram for the Hopkinson test, and in the next video we see about the calculations in the Hopkinson test and field test and retardation test. So coming to the block diagram of the brake test or load test. So this is the block diagram. So this test is also called as direct load test. Direct load test. So what is the meaning of the direct load test means? Direct load test means, so here we can apply the load directly to our motor. Directly to our motor. So based upon that load we can find the performance of the DC motor. Performance of the DC motor. So for that what we do means, we can connect the one voltmeter across the armature and the ammeter ISH, and the for the controlling the main current another ammeter. So two ammeters and one voltmeter we can perform this test, brake test on the brake test or direct load test on the DC motor. So this one is the one pulley, and here we have the two weights, weight 1 and weight 2, and one weight is we can tighten and one weight is we can loosen. So based upon the tight side and based upon the slack side also we can find the performance of the brake test. So let us see what is the test and how we can perform and how we can do the calculations. So in that brake test, let R be the radius of the pulley in meters, radius of the pulley, and N is the speed in the RPM, and W1 and W2 are the spring balances for the tight side and the slack side. So here the W1 is the spring balance reading on the tight side, and W2 is the spring balance reading on the slack side. So when we tighten the one side of the W1, so definitely some brake will be applied to our the DC motor after running or when running. So based upon that we can find the calculations. So the net pull weight on the belt due to the friction at the pulley is difference between the two spring balances reading. So one W is the tight side and SC is the slack side. So the net pull on the rope we can given as the W minus S kgs, W minus S, and there will be some effect on the gravitational effect on that pulley also. So in order to eliminate that gravitational effect, we can multiply this value with 9.81. So the net pull on the rope can be given as the W minus S into 9.81 newtons, and we know that the rotor of the motor definitely has some radius. Why? Because that will be in the form of a circular manner, and the speed of the rotor also we know by using the tachometer. So as the radius r and n is the speed we know, then the soft torque can be given as the net pull torque into resistance. Sorry, not resistance, radius. So net pull into r, radius. So what is the net pull? W minus S into 9.81 into r. So this one is the TSH. So if you know the TSH, shaft torque, then the output equation we can write. So what is the formula for the output equation means, the output power is equal to 2 pi nt by 60. 2 pi nt by 60, this formula already we well known. So 2 pi nt by 60, but here the t is the TSH, and that value can be given as the 2 pi n into TSH means W minus S into 9.81 into R by 60 watts. So this is the formula for the output power. This is the formula for the output power. So we apply some voltage and we can find the current through the ammeter. So the total power given, input power we can write as the multiplication of this voltage and current. So the input power P in can be given as the V into I into watts. So we know the output and now we have the input. So we can simply find the efficiency. So what is the efficiency formula? Output by input into 100. So what is the output? 2 pi nt by 60, where T is the W minus S into 9.81 divided by input is the Vi. So efficiency equal to output by input. So from the equations 2 and 3, the efficiency can be given as the P output divided by the P input. So in this manner, we can find the efficiency of the motor using the brake test. Brake test means direct test. So by applying the direct load, we can find the efficiency. That because of that reason, this method is very exact method. Exact method. So coming to the advantages and disadvantages of the brake test. So first of all, we want to see about the advantages of the brake test. So here basically we have the three types of advantages. So what are the three types means? First one is the actual efficiency of the motor under working conditions to be found out. Why? Because since we perform on the direct loading, so the efficiency we can find is a very efficient one. Efficiency. And next one is, this one is very easy to perform also. Why? Because direct applying the load. And next, it is not only used for the DC shunt motors and compound motors, it can be used for the any motors. That means either series motors and compound motors and shunt motors. Why? Because direct applications of the load is nothing problem. There is no problem. So because of that reason, it is not only used for the shunt motors, it can also be performed for any type of the DC motor. However, in addition to these advantages, we have some disadvantages also. So the what is the best first disadvantages is the belt friction of the is very high in this. So when the because of that belt friction, there definitely there will be some heat will be generated. So some dissipation of the energy is there. So there will be a large dissipation of the energy because of the belt friction. A lot of heat will be generated. And next one is we have to provide the cooling arrangement in order to reduce that heat. So normally in our laboratories we use water as the cooling liquid. And next one is it will be convenient for the small rated machines only due to the limitations regarding the heat dissipation. If you use for the large applications, the heat development is more, so losses will be more. So because of this reason, that may not be sufficient for large rated machines. So this can be limited to only small rated machines only. And next, the power developed gets wasted here because of the braking test. Most of the power will be wasted. So this may not be useful for the many more applications. In case of the heat, for the case of the large machines, this will not be useful for at any case. So these are the disadvantages of the brake test. And coming to the next test, the next test is Swinburne's test. So the Swinburne test is also called as the no load test or predetermination test. No load test or predetermination test. And since we can perform the no load operation here, so the series motor is not applicable for the Swinburne test. Why? Because if you run the series motor in the no load test, there will be a drastic speed of the operation. So we cannot use it for the Swinburne test for the testing of the DC series motor. So in the test, the efficiency of the machine can be determined at any load is predetermined. Predetermined means without using any load. If you know the efficiency of the machine by assume some loads. So such a test is called the predetermined test. So since here we assume the load only, not apply the any load. Without applying any load, we can assume the load and we can find the efficiency at different loads. So because of that reason, this test is called as predetermined test. And in this test, the machine can be operated as either motor or generator, whatever the case. But both the cases we can measure in case of the no load cases, no load operations. So For that purpose, this is the circuit diagram. So here this is the armature winding, and here this is the field winding. So for that we can one ammeter here for finding the main current, and for finding the shunt current, that means field winding current, we can place the another ammeter A2. So by using these only we can measure the entire parameters, that means efficiency, losses, etc. But in this test, the losses constant losses determined by this test are exactly correct losses. Why? Because these constant losses are similar for the no load conditions and load conditions. So that's why in this test we can perfectly determine the constant losses. So remaining losses are we will predetermine. So the test is not a accurate test, not a accurate test. So coming to the calculations of the Suman test. So let V be the supply voltage applied to the motor or generator, and I naught be the no load current read by the ammeter A1, and ISH is the shunt field current read by the ammeter A2. So no load armature current is what? IA naught equal to I naught minus ISH. Why? Because those two are connected in parallel. So our total current I naught equal to IA naught minus ISH. So IA naught equal to I naught minus ISH. Then the no load input power also we can give. Current is I naught is there, and we can find the supply voltage V by using one voltmeter. So if we multiply that voltmeter reading V into I naught, then we get the total input power. So we can get the no load input power to the motor is equal to V into I naught. And copper losses also we can find, armature copper losses. How? Here we have the armature current IA naught, and RA value we know. So the value of the armature copper losses are I naught minus ISH whole square into RA. So we know the armature copper losses and input power. So if you subtract these losses from the input, what we get? We will get the constant losses. Why? Because there is no output there. So because of that reason, input equal to output plus losses. But in the no load test, there is no output. So we can make the output 0. Then input equal to losses. So those losses are nothing but armature copper losses and constant losses. So armature copper losses, we have the formula. So by using this, we can find the only constant losses. So the constant losses can be given as input power V into I naught minus ISH whole square into RA. So with this we can find the constant losses. So from this we can go for our analysis for the determination of the efficiency. In case of the motor as well as the generator. So up to now we find the only constant losses. These losses are very perfect results. Why? Because all are we can measure by the meters, and here we perform this operation in the no load operation. So since the constant losses are known, the efficiency of the machine at any other load can be determined by assuming that load. Suppose it is desired to determine the efficiency of that machine at load current I, then we can assume that armature current equal to IA equal to I naught minus ISH in case of the motor. Why? Because I naught equal to IA plus ISH in case of the motor, and IA equal to I naught plus ISH in case of the generator. So when the machine is running as a motor, the input power equal to what? V into I, and armature copper loss equal to I square RA losses. I square is nothing but in case of the motor we write I minus ISH whole square. So I minus ISH whole square into RA, and constant losses equal to WC equal to we already known VI naught minus I naught minus ISH whole square. So total losses equal to PECU copper losses plus constant losses. So motor efficiency is equal to what? Input power we have, and output equal to input minus losses. So here the input equal to VI, and our losses equal to PCU plus WC. So if you subtract those losses from the input, then we can get the output. So efficiency of the motor can be given as the VI minus PCU plus WC divided by VI. So in this manner we can find the efficiency at any load. So for if we want to find the half load, we can make the armature currents with the load as the x square, where x is the load, but that load is only a predetermined load, not a exact load, and similarly when the motor is running, when the machine is running as a generator. So output of the, so there input of the motor is Vi. So now the output of the generator is Vi. So armature copper losses are same. What are those? PCU equal to I square Ra. That equal to, in case of the generator, Ia equal to I plus ISH. So I plus ISH whole square into Ra. So constant losses equal to V into I naught minus ISH whole square into Ra, which is already we calculated. And the total losses equal to PCU plus PWC. Then the generator efficiency equal to, what is the generator efficiency? Output by input. That means output is Vi. Input is output plus losses. That means what? Vi plus PCU plus WC. So here our formula is somewhat wrong in the slide. So here the generator efficiency equal to output by input. So output we have Vi. So we have the Vi in the numerator. And in the denominator we have the input. So input equal to output plus losses. So that means Vi plus losses PCU plus WC. So this equation is wrong. So please observe that. Here the efficiency of the generator is Vi by Vi plus P copper loss plus constant losses. So this is the efficiency of the generator, and however we can find this for different loads also by placing at the copper loss as x square, where x is the load. That load may be either full load or half load or 1/4 load or 3/4 load, etc. So next, advantages of the Swinburne test. So what are the advantages? The first one is this test is very convenient and economical, as it is required very less power from the supply to perform the test. Why? Because here we can perform this test in the no load operation. So in the no load operation, the power consumption is very low. So it is very convenient and economical for performing. And next, what is the second advantages? Since constant losses are known, efficiency of the Swinburne test can be predetermined at any load. So we can assume the any load, that is half load or 1/4 load or 3/4 load. We can find the efficiency at any load. So these are the advantages. And coming to the disadvantages of the Swinburne test, iron loss is neglected. So there is change in the iron loss from the no load to full load due to the armature reaction. So we consider that iron losses are the constant losses, and those losses are almost all very perfect losses. So however those perfect, there may be some deviation is there. Why? Because in the no load to full load, definitely there will be some armature reaction effect. So because of that armature reaction effect, those iron losses may be slightly different. So with that, the efficiency we determined is not a up to the mark, that is not 100% perfect. There will be a some deviation is there. And in a similar fashion, we cannot be sure about the satisfactory commutation on the loaded condition, because the test is done on the no load. The commutation effect also may not be observed in the no load when compared with full load, but we can we can find the efficiency at different loads by assuming the load. So that is not a perfect value we will obtain compared with the brake test. And similarly, we cannot measure the temperature rise when the machine is loaded. So when the machine is loaded, definitely because of the shaft rotation and the belt tighten, definitely there will be a temperature rise. But in the no load, there will be no problem of the temperature rise. So the power losses with the temperature as also we cannot be identified. So this may not be a perfect efficiency when compared with the temperature point of view also. And in the DC series motors, that Swinburne test cannot be done, I already told, to find its efficiency, as it is a no load test. So we does not run the series motor in the no load. Why? Because the speed of the motor will be drastically high. So in order to perform the no load test, it will be very dangerous to the machine. So we cannot perform the Swinburne test to the DC series motors. So in order to find the no load operation with a better accuracy or better efficiency, what we have to do? Then we have to go for the another test. That another test is called the Hopkinson test. So here, instead of connecting a load, we can use the generator and motor. Both are no load operation, and both are back to back connected. So with this, what we do means, the generator will be, the motor will be acts as a load to the generator, and the generator will be acts as a source to the motor, like that. So in this manner, some losses will be, we can perform the no load operation with load symptoms. So with this, we will get the efficiency somewhat better than the Swinburne test. However, this test in detail we will see about the next video. So in this video, we comprise our discussion only to the brake test and Swinburne test. So in the next video, the calculation point of view of the Hopkinson test and the field test and retardation test. Thank you.